Good morning, children. Today we will study about the properties of the solid. यहाँ पर हमें दो प्रॉपर्टीज़ के बारे में स्टडी करना है. एक तो इलेक्ट्रिकल प्रॉपर्टीज़ है, दूसरा मैग्नेटिक प्रॉपर्टीज़. इन इलेक्ट्रिकल प्रॉपर्टी डिपेंडिंग अपॉन द conductivity of the solid, whether they can allow the passage of electric current through them or not, they can be divided into three types. One is conductor, and another is insulator, and third one is semiconductor. Now the conductivity of conductor ranges from 10 to power 4 to 10 to power 7 ohm inverse meter inverse. In case of insulator, the conductivity is too small, it is extremely low, it is hardly of any importance for electrical conductivity. Its value is 10 to power minus 20 to 10 to power minus 10 as plastic and glass. In case of semiconductors, the conductivity ranges from 10 to power minus 9 to 10 to power 3 ohm inverse meter inverse as silicon and germanium. Now if we take the conductor again, so conductors means which can allow the passage of electric current through them. They can be divided into two types. One is metallic conductor and another is electrolytic conductor. In metallic conductor, the conduction of the current is by the movement of electrons. As we know that metal atoms are larger in size and their electrons are loosely held by the nucleus, so they can easily delocalize inside the metallic crystal on application of potential difference. So that's why, since their conduction is by means of movement of electrons, so they are called metallic conductor. And with increase in temperature, the conduction of metallic conductor decreases. This because अगर हम टेम्परेचर बढ़ाएंगे तो जो मेटेलिक कंडक्टर है उसकी लेंथ बढ़ जाएगी, रेजिस्टेंस बढ़ जाएगा और कंडक्टेंस कम हो जाएगा. इलेक्ट्रोलाइटिक कंडक्टर्स के बारे में अगर हम बात करें, सो आयनिक कंडक्टर्स आर कॉल्ड एज इलेक्ट्रोलाइटिक कंडक्टर्स. They can conduct electricity only when they are in molten state or in aqueous solution. So there the conduction is due to movement of ions, so that's why they are also called as ionic conductor. Their conductivity increases with the temperature. So as if we increase the temperature, then different types of interactions get loosened and movement of ion increases, which can increase the conductivity of electrolytic conductor. In case of electrolytic conductor, they cannot conduct electricity in solid state because ions are very strongly pulled, very strongly held up. So since they cannot move, they cannot conduct the electricity. But in case of metallic conductor, they can conduct electricity in solid state as well as in molten state. Here is band theory to explain the conduction in metallic conductors. So how the band theory can be used to explain the metallic conductor? First of all, we should know what band theory is. Actually, this band theory is also called as molecular orbital theory. This is based on the concept of molecular orbital theory. So if we take the case of any alkali metal, say for lithium, so as we know in conduction only electron present in valence shell, they participate. Inner core electrons, they do not participate in conduction of electricity. So we will focus here, we will concentrate ourselves to the electrons present in valence shell only. Suppose we have only one lithium atom, so its electronic configuration of valence shell is 2s1. It means only one electron is present in the valence shell of the lithium atom. So in order to combine, there must be at least two lithium atoms. So when two lithium atoms undergo linear combination, they form two molecular orbitals. One is sigma 2s and another is sigma star 2s. Now the number of electrons available from these two atomic orbitals in the valence shell only two. One from this lithium atom, another from this lithium atom. So since number of electrons are only two, so they will occupy the lower energy orbital like sigma 2s, and sigma star 2s will remain empty, and these two are the molecular orbitals belonging to the same 2s energy level of the combining atoms. Now if similarly, if n number of lithium atoms combine, so they form n molecular orbitals. Now these molecular orbitals are very closely spaced, and these molecular orbitals are called energy bands. As we know, the half of the molecular orbitals contain valence electrons and another half of the molecular orbitals are empty. So similarly, if there are n number of molecular orbitals, so n by 2, that is half molecular orbitals are filled, they contain the valence electrons, and another half molecular orbital within the same energy level, they are lying vacant. So the molecular orbitals which contain valence electron, they constitute the valence band, and the lowest lying empty molecular orbitals constitute the conduction band. Valence band क्या है? Molecular orbitals containing valence electron. Conduction band, empty molecular orbitals lying above the valence band, they are called conduction bands. Now if we see the case of lithium, so there is no energy gap between valence band and conduction band, as both are belonging to the same energy level. So on applying the potential difference, the electron can easily jump from valence band to conduction band and they can conduct the electricity. No energy gap between valence band and conduction band in case of alkali metal. But what happens in case of alkaline earth metals? They are also good conductor. Let us see and try to explain the conduction by any alkaline earth metal. So suppose we have the case of beryllium and its electronic configuration of valence shell is 2s2. Okay, so it contains 2 electrons in its valence shell. Now when two beryllium atoms undergo linear combination, so they form 2 molecular orbitals, as the number of molecular orbitals form equal to number of atomic orbitals combined. So now the number of electrons available from 2s energy level 4. So it means sigma 2s is filled and sigma star 2s is also filled. Now no empty orbital is seen to be present here. So how beryllium or magnesium or any alkaline earth metal can conduct electricity, although they are very good conductor? So this can be explained on the basis of overlapping energy bands. So how the overlapping of energy band can be explained? Suppose n number of beryllium atoms undergo linear combination. So molecular orbitals are formed corresponding to 2s energy level and also corresponding to 2p energy level. Some of the molecular orbitals of 2p energy level possess energy which is equal to some of the molecular orbitals of 2s energy level. So the electrons which otherwise filled, electrons from 2s energy level, some of the electrons of 2s energy level which is otherwise filled, shift to some of the molecular orbitals of the 2p energy level. So this shifting, because these are this constitute the energy overlapping bands from here to here, they are overlapping because their energies are similar. So some electron transferred from 2s energy level to 2p energy level, and this results that the 2s energy level becomes partially empty, otherwise it is filled, and 2p energy level partially filled, otherwise it is empty. So what happens within the same energy level, now some of the molecular orbitals get empty and constitute the conduction band. So on applying the potential difference, these electrons can easily jump in this way from here to here, from here to here, and when this become empty, from the source the electron comes in. So in this way the conduction is noted in case of alkaline earth metal, and it can be explained. Now if you take the case of insulator, there will be a great large gap in between valence band and conduction band, so they cannot conduct the electricity, as electron cannot easily jump from valence band to conduction band. What happens in case of semiconductors? The energy gap is intermediate between this insulator as well as conductor. So some of the electrons may jump from valence band to conduction band, but this is hardly of any importance. This is very low value. But if we increase the temperature, then more number of electron can jump from valence band to conduction band, and the conductivity of semiconductor increases. Sometimes the conductivity can be increased by doping, by adding the impurity of 13th group or 15th group, as you have seen. Suppose this is the case of silicon. So this is 14th group material, base material, and it is topped with some 13th group impurity like boron or gallium. So what happens when gallium is added to this one? So then, since gallium has only 3 electron, then electron deficient bond is created. So gallium occupies the space just above the valence band like this. Now since valence band is here completely filled, once the gallium comes and makes a bond with the silicon atom, then this creates one electron deficient bond, that is hole. So electron now start jumping from this valence band to this hole that is given by the gallium, and in this way the conduction is noted. Similarly, if we add 15th group impurity, maybe like phosphorus or arsenic, then they combine with the silicon atom and form a band that is near the conduction band. So since this is the phosphorus or arsenic, so it contains one extra electron. This combined with silicon atom and minimize this gap in this way that this is nearer to the conduction band. So since, as we know, that this has one extra electron, so when potential difference is applied, then this electron, that is extra electron, excess electron of this 15th group atom, that is P or arsenic, then this jumps into the conduction band. Now this become empty, so from valence band electron comes over here. So in this way the conductivity get increased when the semiconductor or silicon is topped with 13th group or 15th group material. So in this way the conductivity can be explained by using the band theory. Now another property is the magnetic property. Depending upon how the solid behave in external magnetic field, solids can be classified into 5 types: diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and perimagnetic substances. In case of diamagnetic substance, so they are characterized by the filled orbitals. So they are repelled by the magnetic field, external magnetic field like NaCl, and titanium dioxide is diamagnetic substance. Paramagnetic substances, they are characterized by the orbitals having some unpaired electrons. So they are attracted by the external magnetic field as cupric and chromium 3 positive ion, like that. In case of ferromagnetic substance, the magnetic moments which are formed by the grouping of atomic magnets inside the substance. These magnetic moments of the domains, they are aligned in a parallel fashion in one direction only. So this results into very high degree of magnetism, and these substances, once they are kept in external magnetic field, they become permanent magnet. Means their magnetism persists even if the external magnet is removed from the site. For example, if you take the case of iron, nickel, cobalt, in all these cases, once they are magnetized, they become permanent magnet because of the alignment of magnetic moment of the domains in one direction in parallel fashion. In case of anti-ferromagnetic substance, we expect to have very high degree of magnetic moments from the domains. But actually, the arrangement of domains, magnetic domains, is in compensatory manner in parallel and anti-parallel direction. So this results the zero resultant magnetic moment. So once the magnetic moment becomes zero, so the actual magnetism obtained is less than what is expected from the magnetic moment of the domains. For example, manganese oxide and manganese dioxide. In case of paramagnetic substances, if you see, then alignment of magnetic moment of the domains is in non-compensatory manner, means parallel and anti-parallel in unequal number. So they have some resultant magnetic dipoles. So for example, as Fe3O4 and ferrites, they are paramagnetic substances. Thank you.